We are going to use angular momentum to solve a rotational collision problem. So we conserved momentum previously when we were doing linear collisions where you had one object bumping into another and sometimes they moved together, sometimes they bounced apart. So now we've got this new setup where you still have two objects that are going to eventually interact with each other, but then we're going to have this rotational thing to consider. So a 34 kilogram child runs with a speed of 2.8 meters per second, tangential to the rim of a stationary merry-go-round. And then I've drawn an above view for that. So if the merry-go-round's spinning this way, then the child's going to jump onto the rim of that. The merry-go-round has a moment of inertia of 512 kilogram meters squared and a diameter of 4.62 meters. When the child jumps onto the edge of the merry-go-round, the entire system begins to rotate. And the goal is to solve the final angular speed of the system. So if you think back to when we were trying to identify setting up types of collisions when two objects interacted, we have a child that's running, the child has some momentum, and then the child's jumping onto something that's stationary. So we solved that like a perfectly inelastic collision. You have two objects separated in the beginning, and then they move together as one. So the clue here is that the child is jumping, this is stationary, but they're jumping tangent to the rim. So if the child's kind of running in here, kind of running in this direction, then they're going to land kind of right on the outside there, tangent to that, tangent to the merry-go-round. And then right when the child lands on the merry-go-round, they start to rotate together. So if we have to look at the forms of momentum, forms of angular momentum that we can use, there's kind of two versions that Dr. Wu talked about in the previous video. One is that angular momentum is R cross P, relationship between the radius and the linear momentum, and then also L equals I omega. This was your moment of inertia and the angular speed. All right? So if I think about the before case, we've got a child that's just running tangentially, so there's not really a rotational piece of that yet. So we kind of have to think about it as a tangential velocity that's right in line with this radius here. So I'm going to look at this piece with the linear momentum in it because it seems to be a little more of a linear thing at that part. So I have my radius. And then linear momentum we know is just mv. So that'd be like the mass of the child, the speed that the child, the velocity that the child's running. If we think about the velocity, the cross product wants that perpendicular relationship. So if we look at the relationship between the tangential velocity and the radius, that's going to be a 90-degree angle there. So this will turn into r mv sine theta. And then that theta there is 90. So the sine of 90 would become 1. So what we end up getting here for the initial momentum right before they start to move together is just mvr. I usually like to write the mass first. So just multiplying these together, so it's times 1. Okay, so now we have a relationship for the initial angular momentum of our almost collision. Just getting ready to start moving together. So we've got the magnitude of angular momentum, because that sine 90 was 1, turned out to be this Li equals mvr piece. So if we want to use this idea, we need to conserve momentum. So I'm going to try to find a relationship for the after part, the final momentum. So if I think about what's going to happen right when the child's on the merry-go-round and then they start to spin, okay? So we will have two objects that are rotating at that point. Our merry-go-round's going, and then the merry-go-round, remember, had that moment of inertia of 512 kilogram meters squared. So that will be spinning with some final angular speed, which is actually what we're looking for. So if I think about our two objects here, the merry-go-round, I'll call it MGR for short. The merry-go-round is going to be moving with this relationship for angular momentum, but then we also have to consider the child that, I'll draw this on a different place, the child's up here now on the outside also continuing to move around with the same final speed, angular speed. And the r is going to be out here. So what we can do is actually treat that like a point mass. So instead of having some number given for the moment of inertia, we just have a small, it's kind of like a small point on the outside of this big object. And that's where we defined mr squared before for just a like a small point mass. So we can treat the child like a point mass here, okay? So then for the child, you'd get mr squared times omega, where this is the moment of inertia. So here's our child and our merry-go-round moving together, and that's a relationship for the final angular momentum of the system. And we know that's going to be conserved, so now we can start doing some algebra, setting these two pieces equal to each other. So we get mvr, where m's the mass of the child, and then since these guys are the same variable that I'm trying to solve for, I'm going to go ahead and factor it out to make it a little bit easier to deal with algebraically. So we'd have I plus mr squared times omega. And then you can divide by this piece. So you get I plus mr squared. And then dividing on this side would just cancel that out. So I can just go ahead and move this. And then we have a relationship for the final angular speed. So if we look at all the values that were given, we've got 3.4 kilograms for the child. So 34, excuse me. We can plug that in for mass. So we'd have 34. Velocity, that tangential speed that the child was running with, was 2.8. So I can multiply by 2.8. The diameter of the merry-go-round was given as 4.62 meters, so I have to cut that in half, so it'd be 2.31. And then I was just 512. And then 2.31 squared. And by the time you calculate that, you should get something like 0.317 radians per second. And there you have it. You can do this whole conservation of momentum thing with collisions using angular momentum, where things spin. See you in the next video.